Rust's borrowing rules get in the way, and like a lot. Sometimes code seems so beautifully crafted, but the borrow manager just doesn't agree. So what if I told you that there's a way around the borrow manager, and that it's actually in full agreement with Rust's best intentions? Let's take a look at a RefCell today. In order to create some setting here that is kind of realistic, let's say that we have some expensive computation that we would like to cache because it's so expensive, right? And here, of course, the expensive computation is in fact just formatting a string, but hey, insert any computation you like here. In order to set this up, I decided to go with a struct called cached computation. Inside, I want to keep a hash map that maps from my input values, which are U32s, to my output values of the computation, which are strings. Then let's take a look at what the implementation for the cached computation will be. Of course, we got a new function, and we got another method that is supposed to get the actual value, which will either execute the expensive computation if the value is not cached already, or it should access the cache if the value is cached already. So if you look at the main function down here, we will try this in the following way. We want to compute 3 values. Our input is 1 for one time, but we use 2 twice. And therefore, the second time we use 2 as an input, it should access the cache rather than execute the expensive computation. Of course, the meat of this all, what this is all about, is the getValue method. So let's get to implementing it. So the first thing I want to check is whether I am missing this value in my cache, i.e. it has never been computed for this input. If we are actually missing the value in the cache, we'll have to do the expensive computation. There's no way around that. However, we definitely should make sure to insert this newly computed value as a key value pair into our hash data. And then, of course, in the end, whether we had this value in our hash map or not, we definitely need to return the data here. I chose to go with a clone of the string just to make things a bit simpler for this tutorial so that we don't have to use any references with lifetimes. Now you might already see the problem here. The borrow manager is complaining that we cannot borrow self data as mutable because it is behind an immutable reference, which we can see at self. So this method takes an immutable reference to self. Therefore, we're not allowed to mutate any of the state inside the struct. Oh, what a beginner mistake, you might say. Just take a mutable reference to self, and the problem is already done for. Okay, so let's now follow the suggestion of the compiler, which is to take a mutable reference to self in the getValue method, and therefore the borrow manager doesn't complain anymore in this method. However, now we have a different problem. Of course, our cache now has to be mutable in the main function. You might say that this is not a big deal, because in this example it actually isn't. However, bear in mind that a mutable reference is unique or has to be unique, i.e. while we are holding a mutable reference, we cannot have any other reference anywhere else in the code, whether mutable or immutable. Meaning that if we would like to use this cache at multiple places in our code, it won't work anymore like this because we only can have one mutable reference, one mutable access to this cache. So we see that taking a mutable reference to self or getValue is actually going against the idea that we want to use this cached computation just like the expensive computation function itself. And the expensive computation function does not have any restrictions at all on its usage. It can be called from anywhere because it's a static free function. And therefore, I will fight the borrow manager to compile the getValue method with an immutable reference to self. The name of the function already implies that getting a value should not require mutability. So, what gives? We're now just gonna trick the borrow manager by setting some cheeky compile flag. Borrow. We are going to write fully legal and idiomatic Rust code, and still alter the self behind an immutable reference. For this, we will leverage RefCell. So in order to start off with RefCell, of course, we need to import it first. RefCell is actually a generic over T, where T can be basically any type. So let's start by wrapping our hash map in a RefCell. And now we get to the interesting part. What we can do now is we can access this data or borrow it in a mutable way. by calling the borrowMut method on our RefCell. And as you can see here, even though the get value still takes an immutable reference to self now, we can call borrowMut on the data, and what we get out of this is something that is very similar to a mutable reference called a refMut. And to show you that this works, we can now work on this data object rather than self.data. And you can see that all the compiler and borrow errors go away. So it seems like Rust lets us off the hook with borrowing rules here. And in fact, when we run the code, we can see that we get exactly the result that we intended to have. We call the cache get value with the value 1, the input 1, and it does the computation. We call it with input 2, it does the computation. We call it again with input 2. It doesn't do the computation, but instead it accesses the cache and returns the already pre-computed value. So functionality seems to be 100% there. So let's play around with this a bit more. Instead of accessing the mutable data to return the value, let's try to use this other method, not called borrowMut, but borrow. And borrow again here from self.data in order to return the value. Let us first build this to see that everything seems to be okay at compile time. And let's now run it. And isn't that interesting? Even though our code fully compiled, we get a panic saying that we have an already mutable borrow on this self.data, because the panic ensues in line 27. And it seems like we cannot borrow it again. Oh my, a borrowing error at runtime that resulted in a panic. Wasn't that what Rust was supposed to protect us from in the first place? Well, yes and no. By using the RefCell, we took the burden of following the borrowing rules on ourselves, rather than trusting Rust to find any violations at compile time. And what we did here is a violation. While a mutable borrow exists, it has to be the only borrow of the data. So when we call self.data.borrow here, we violate this rule. So let's be good Rust citizens and create a scope so that the mutable borrow is dropped before the reborrow occurs. And lo and behold, this code not only compiles, but runs without panicking now. And it's doing exactly what we want. Okay, the fact that Rust lets us do this is actually wild somehow, considering that safe borrowing is one of the cornerstones of this language. Well, it just so happens that the compile time borrowing rules are very, very strict. And on top of that, the compiler enforces them very conservatively. And so, some of the programs that are actually correct don't compile. And the initial example is one of them. Let us take another look at the initial program. Because this is a single-threaded program, getValue can never be called concurrently. The method returns a cloned value, so the variables in the main function don't hold any references to entries of the cache, which would be invalidated. So inserting another value into the cache while in the getValue method will not lead to any undefined behavior, like dangling references or unexpected mutations. So the language needs a way to get around the strict limitations of the compile time borrowing rules. And this is where interior mutability comes in. The RefCell we just used was one of the tools that allows us to access the wrapped value in a mutable way, even though the RefCell itself is behind an immutable reference. And that's probably why it's called interior mutability. We can mutate whatever we wrapped inside of the RefCell. With interior mutability, we can get by the rules of compile time borrow checking, but we take the responsibility on ourselves to obey the borrowing rules at runtime. And we already saw what happens if we break these rules. The program panics and crashes. This is, of course, way worse than getting a compiler error. So you should use interior mutability only when you absolutely need to. So now we saw how to use RefCell to leverage interior mutability. But aren't you curious now how this allows us to sneak past the compile time borrow checking? Well, I've got you covered. Let's take a deep dive and look at the code in the standard library. But before we do that, let me quickly introduce you to another method of building a real deep understanding of technical topics. With the sponsor of today's video, Brilliant. Brilliant helps you get smarter every day with thousands of interactive lessons in math, science, programming, data science, and AI. I am a very avid learner myself, and as such, I get a lot of joy out of building a deep understanding for complex topics, and software engineering is one of those topics. And for me, there's nothing quite like the moment where things actually click. And Brilliant allows me to incorporate learning new skills into my daily schedule. What I specifically like about Brilliant is that the lessons get to the point quickly, rather than spending time to have a lengthy explanation that nobody really needs. Instead, you get hands-on exercises and some great visuals to go along with it. Additionally, Brilliant fosters my critical thinking skills with an interactive method. And this builds my problem-solving skills, which are way more important in real life than just having memorized a few key aspects. To try everything that Brilliant has to offer for free for a full 30 days, visit brilliant.org/greenteacoding or scan the QR code on screen. Or you can click on the link in the description. You'll also get 20% off an annual premium subscription. And now, back to our deep dive into the inner workings of RefCell. Okay, so in order to understand this, let's go right to the source. All of the code we are interested in is inside cell.rs. The RefCell struct is a generic over T, where T is the type that is wrapped. As I said before, it can basically wrap anything. Doesn't even need to be sized. Inside we have three members. Let's discard this borrow at right away, because all this is providing some debug information, and we're not really interested in that when we want to look at how RefCell works. Let's look at the value field instead. This is what's storing the actual wrapped object. It is wrapped again in an unsafe cell, which is another type that provides interior mutability, but, well, in an unsafe way. But no need to worry, we're not directly working on that cell as the users of RefCell. However, just take note that this will, in the end, take ownership of our value of type T. The really interesting field here, though, is borrow, which holds a borrow flag, again, wrapped inside an interior mutability container, this time a cell. If we take a look at the borrow flag, this is nothing more than a type alias for an isize, probably for reasons of type safety and readability and whatnot. Additionally, a constant unused is defined as 0. From the comment above, we can see that positive values represent the number of ref active. So this is a counter for immutable references if it is greater than 0. However, if it is less than 0, so negative, it represents the number of ref mute active, which is another way of saying this is the number of mutable borrows that we could have. And then it goes over how it's even possible to have multiple ref mutes, which we're not going into today. So even though we don't yet know what these types ref and ref mute are, those suggest that they are something akin to an immutable and mutable reference. On top of that, we have two free functions called isWriting and isReading, which reflect this invariant called in the comment. If whatever value we have in our borrow flag is less than unused, and unused again is 0, then we are writing, so we have a mutable reference. Otherwise, if it is larger than unused, we have a reading reference, so an immutable reference. Let's now take a look at the new method. Well, this is really quite straightforward. Of course, we're returning a RefCell T, as is convention in new functions. And all we're doing is we wrap our value inside this unsafe cell. We create a new borrow, which is initialized with a borrow flag of value unused, so it's 0. And again, this debug information we're not really interested in. So now let's try to get after the meat of this stuff, borrowing mutably. So borrow mute is exactly the function that we called to do this. And this method notably works on an immutable reference to self, just as we would expect, because we called it behind an immutable reference to a RefCell. And it returns something that probably resembles a mutable reference by the name of it, and it's called refmute. So this is exactly what we would expect for interior mutability, working on an immutable reference to self and returning something that is a mutable reference. Don't worry, we're going to get into what the refmute actually is later on. The method itself is quite short. it calls a try borrow mute, which apparently returns a result. And if that result is okay, we'll just return whatever is contained in there, which by the looks of it is a ref mute. And if it's an error, we are gonna panic that this is already borrowed. So this is where the panicking comes in. And that's why we need to be extremely careful to not violate the borrowing rules at runtime. Well, we have two loose ends now. Number one is, what is ref mute? And number two is, how does try borrow mute work? So, for better or worse, let's drill down the function calls now and get back to ref mute later. Okay, so let's drill down one layer. Let's look at try borrow mute now. This works on an immutable reference to self, again, just like borrow mute. And again, we have to match here, this time on an option returned by borrow ref mute new. So this is a new function that returns an option to a borrow ref mute, which is again a type that we are not really familiar with yet. This borrow ref mute new takes in a reference to our borrow, which we know contains the borrow flag, which in fact is a count of immutable and immutable borrows. So if the option contains none, this is the bad case, try borrow mute returns an error. Well, with some debug information in there that we're not really interested in. And this, as we already saw, when it gets returned to borrow mute, will cause the panic. If we get some though, we return a ref mute, wrapped inside an OK. The ref mute contains a non-null pointer, here, to the value being borrowed, together with a borrow ref mute, called B here, and some phantom data as a marker. So it seems that we have to drill down one more layer, to borrow ref mute new. So we're here at borrow ref mute now. What this struct holds is actually a borrow again, which is a reference to a cell which contains the borrow flag. So again, this is the information, how many borrows we currently have. And if we are looking at the new method, we see it in fact returns an option with a borrow ref mute of lifetime B inside. And this is where it actually gets interesting, where the actual logic happens behind all of this wrapping. We match here on the current number, the current value that is stored inside our borrow flag. If it is unused, meaning it is 0, we can then set it to unused -1, meaning that we'll take out a mutable reference and therefore we'll decrement the counter by 1. And this is the happy case, so we return some of a borrow ref mute inside, and the borrow ref mute gets initialized with this borrow reference. So happy case is there is no references in there, so therefore we can create a mutable reference, which exactly corresponds to the borrowing rules that we would also have at compile time, which say that if you want to have a mutable reference to something, no other reference to that same type are allowed. In all other cases, whether we have already another mutable reference or any number of immutable references, we will return none, which, again, if we bubble that up through try borrow mute and borrow mute, we will get a panic in the end. So now, back to our final challenge, the one loose thread we still need to reel in, which is ref mute. Ref mute is again a generic over T, and it has this lifetime annotation B in there. And we should take note that the T is also restricted by the same lifetime B. Inside, it does hold a non-null pointer to the T, where the object of type T is the one wrapped inside and owned by the RefCell. You could ask why we are using a non-null pointer T here rather than a mutable reference. Well, the nota bene says we use a pointer instead of a mutable reference to T to avoid no alias violations, because a ref mute argument doesn't hold exclusivity for its whole scope only until it drops. So if you look up this no alias stuff, you'll find that it is some LLVM optimization, which only holds true when we can make sure that throughout a certain scope, there is only ever one reference to this value. This is something that it seems like we don't want here, because we want there to be possibly another reference inside the same scope, if the first reference already has been dropped. And therefore we're not using this mutable reference to t, because that again would trigger this exclusivity via no alias, but instead we use this non-null pointer, which for all intents and purposes is just a pointer that is never null. The refmute, besides the value, holds also a borrow, which is the borrow refmute, and it also goes over this lifetime of b. Why is that the case? Well, because the borrow refmute has inside it a borrowed version of the cell, in which again we have our borrow flag. And in the end we have this marker of the phantom data, and this is where it gets kind of weird. And if I say weird, what I mean is actually quite complicated. If we read this comment here, it says non-null is covariant over t, so we need to reintroduce invariance. And I could try to explain variance at this point, but I don't think it adds anything for our understanding of RefCell and refmute. Therefore, I'll keep it very short. Without this marker here, RefCell would inherit the variance of an immutable reference, which is covariance, as it says here. However, this would mean that the compiler could not catch some use after 3D errors when using a refmute. Therefore, we place a marker in it that is annotated with a mutable reference of lifetime b. This makes the compiler derive the variance of a mutable reference for refmute, which is invariance, thus making it safe to use. So let's keep it at that for variance today. What we learned so far is that the RefCell itself takes ownership of a type of t and tries to create a refmute, as we see here, when we call borrow mute. Internally, it keeps track of how many borrows, mutable and immutable, are currently active, and panics if the borrowing rules are not followed at runtime. If we are not violating any rules though, we will obtain a refmute, which in turn holds this non-null pointer to the data inside the RefCell and the borrow flag. We are now very close to understanding how borrowing mutably from a RefCell works, but there is one more missing piece to the puzzle. What does refmute need this borrow refmute for? Well, when our refmute is dropped, the borrow refmute is of course also dropped. The trick here is that it implements the drop trait, and inside its implementation, the borrow flag counter is again incremented. Because remember that when we created a refmute, the counter was decremented to indicate that we have a mutable borrow. So incrementing it will reset it back to unused. And so that's how the reference counter updates when a refmute goes out of scope. And therefore, once the first refmute goes out of scope, you can borrow mutably again. Now let us wrap up this session. Under the hood, RefCell uses reference counting to check whether we are obeying the borrowing rules at runtime. And if not, it will panic. And this is what gives us the freedom to circumvent the compile time borrowing rules. If this video was helpful to you, well then leave a like and consider subscribing for more valuable Rust content. And leave a comment whether this format where we first look at the usage of some concept in Rust and then do a deep dive into its inner workings is something you'd like to see more of. But now, go and break some borrowing rules. I'll see you next time with Green Tea Coding.